Okay, thanks everyone. So I want to talk a bit about Ignition, which is a new interpreter which we're building for V8. So my name is Ross McIlroy. I'm part of the Chrome performance team in London, and along with Ryan Hodson and Maitri Ali, who are both here, we've been working on Ignition, a V8 interpreter. So first off, I just wanted to give a bit of background of the life of a JavaScript script in V8 as it is now, and what some of the problems might be that we want to address with Ignition. So say you have this script. You load it into your web page, and Chrome decides to parse and compile the script. And the first thing that it needs to do is run the top-level code of the script. So what is the top-level code? Well, pretty obviously, that is some top-level code that needs to be run initially when the script's loaded. But there's also a bunch of other codes. So this code here, here, where we're defining the function names, we're creating effectively global variables for those function names with particular names, updating prototypes on objects, etc. So this is the code which needs to be run initially. So we parse the script, and we compile a big block of code, and V8 doesn't have an interpreter. So we compile machine code for this code, and we run that code. And to do that, we feed the code into the parser into full code gen, which is our first level JIT. So that's a pretty simple compiler. It basically just tries to spit out code as fast as it can. It doesn't do any kind of fancy optimizations. And it produces this unoptimized code from the parsed JavaScript that you give it. So you end up with this. And to get that, you basically needed to parse the whole script. So we have pre-parser and a parser in V8. So we try to only pre-parse the parts of the script which we're not going to execute. So those would be the internal body of functions and things like that. But we do need to pre-parse it because JavaScript, there can be errors that are early, syntax errors that need to be thrown when the script is loaded. Or you need to analyze the scope and work out if you need to track particular variables that might be captured within internal functions, and work backwards from that as to how you actually allocate those variables in the outer scope initially. So we've parsed the whole script once. We've compiled a big block of code, and we start running that code. First thing we do is we call new person. So now we need to compile this new person code. So we have a lazy stub there that as soon as you hit that function, you say, OK, we've not compiled some code for that. Let's compile the code. And of course, to do that, you need to parse that function. So we're effectively parsing that function twice at this point. And we've generated a whole bunch more code. And we continue going on. We'll call this do work function, which calls foo and done. And we end up compiling the set of functions that we execute. So in this case, we've managed to avoid compiling the unused function there, and we've not generated any code for that function. So that's good. But to do that, we've effectively parsed the whole thing twice, the whole script twice. And then it gets worse, because here foo and done are in a loop. So V8, if that loop takes a long time, V8 probably decides, oh, well, you really want to do those foo and done functions. We should do some extra work to compile them with some good code, to optimize the code, and get them running really fast. So we'll parse those functions again. We'll compile some optimized code for them, and we have this extra code. Unfortunately, we can't chuck away the unoptimized code, because the way JavaScript works, it's so you can do anything in JavaScript. You can monkey patch things, change the semantics behind the compiler's back. So it might have assumed that a particular parameter or variable is an integer, and then later you give it a string or an object. And so it needs to effectively back out and say, OK, this optimized code doesn't work anymore. I'll de-optimize to the unoptimized code, which can handle everything. And then later on, we might try again with some extra type information. So that's the basic life of a script. You can see we've parsed everything twice or 3 times, generally, to actually run that code. So just to give some background on how the compiler pipeline looks here. So the optimizing side is effectively another branch on this that we take the source again, we parse it, and then we feed it into one of our 2 optimizing compilers. So we have Crankshaft and Turbofan. Both are used for different types of JavaScript code. Turbofan mainly for ASM.js code, but some other situations, like ES6 code. And Crankshaft is our older compiler, but it can generate fast code for a lot more of the JavaScript language. And then the optimizing code might have to de-optimize back to the unoptimized code. So what's the problem? Well, one of the big problems here that was the initial reason that we started working on Ignition is memory. So we compile big lumps of code for all those functions. That top-level code, that's run exactly once and can never ever be run again. And we compiled a whole bunch of machine code to make sure that we could run that. And it'll stay about in the V8 heap for a wee while. So this is some numbers across from the wild back to from real users. And we see that generally between 30 to 50% of the renderer process's memory is taken up by V8, the V8 heap. And within that, about 30% or so of the heap is taken up by this JITted code that we compile on demand for functions. So there's a fair proportion of the renderer's memory that is locked up in this code, between 10 to 20%, which is a reasonable amount. Startup speed. So this is using a cool tool that Camille and I think Toon's going to talk about it later today or tomorrow, which splits out the various types of execution that V8 does in order to run the scripts on a page. So this is across 25 typical pages on the web, and it's basically measuring what we do to get the page loaded and interactive. So we're spending 33% of the time in the orange block here, the parsing, and the yellow block here, the compiling. We're spending a much smaller proportion in this pink thing here, which is actually executing that code that we've compiled. And there's other bits that are to do with executing, but they're not executing that code that we're actually compiling. So we're spending much more time compiling and parsing the code than we are actually running that code in the first place. So this is a problem. And finally, complexity. So we have 3 compilers. They all get their code from they generate their code based on this abstract syntax tree. That's effectively the source of truth between them. And they all need to interoperate with each other. So full code gen generates some unoptimized code. And sometimes V8 might want to decide to optimize the function that you're running right now. Say you're in a tight loop, and V8 wants to optimize while you're still running in that tight loop. So we can jump from unoptimized code into optimized code. It's called on-stack replacement. So we basically need to be able to figure out how to do that jump, what is currently sitting on the stack in order to do that, and how to introduce that to a stack frame for the function that's running in the middle of its execution. And similarly, I talked about de-optimization, which is the same going backwards. You're in the middle of optimized code. Your stack layout will look completely different from the stack layout of the unoptimized code, but you now need to jump back to that unoptimized code, rebuild the stack. And to do that, because the common source of truth is this abstract syntax tree and nothing else, you need to effectively, these compilers need to effectively interpret or understand what the full code gen compiler would do for each of these abstract syntax tree operations in order to do that. So this is why we built Ignition. So Ignition is a JavaScript bytecode interpreter for V8. And why write an interpreter? Right? V8 is fast. Interpreters are slow. What are the benefits? So it tackles those problems that we saw before. So there's reduced memory usage. So rather than compiling to machine code, we're compiling to a concise bytecode that can be much smaller. And so we can reduce the memory usage, particularly of functions that are not executed very often. We can reduce the parsing overhead. Probably not in the way you think. This is a bytecode compiler, so we are bytecode interpreter, so we are still compiling to bytecode. We still need to parse to do that. But the bytecode is concise, so we can avoid that whole optimization that we do of trying to only compile code that we know is going to be executed, and therefore have to lazily parse the code again when the code is actually executed. We can just take the whole script, compile everything to bytecode, and then we parse it once. And then we can reduce the compiler pipeline complexity. So the bytecode now becomes the source of truth rather than the abstract syntax tree. That's kind of a lower level. And it allows simplification of the optimization, de-optimization pipeline in V8. So this is what our pipeline looks like now. And this is what we want to move to in the future. So now the source comes into the parser, Ignition generates bytecode based on that source, and then the bytecode is the source of truth for the optimizing compiler, turbofan optimized code, and it can de-optimize straight back to the bytecode. And because it used the bytecode to generate the optimized code in the first place, it knows exactly how that bytecode would be interpreted. Unfortunately, we have this. It does actually work, but it's not yet shippable. And the reason it's not yet shippable is because turbofan is not yet fast enough on real-world JavaScript pages that we care about. It was built initially for ASM.js, and it supports the full JavaScript language, but we still need to do some optimization work to make it as fast as Crankshaft. So we need to add back Crankshaft. And unfortunately, Crankshaft doesn't have a front end that we can feed the bytecode into, so we now need a parser in there to generate that. And unfortunately, because it needs this parser, it can't de-op back to the bytecode. So we need full code gen back in there as well. So we're simpler, honest, yeah, simpler. And less parsing. You see 3 instead of 2. Less code, obviously. Yeah, honest. We are going to get to this eventually, but in the meantime, this is our current pipeline. Internally, we call it the Franken pipeline. And we'll gradually get there. So before going into the kind of higher level of how we get to those memory improvements and stuff, I just want to take some time to deep dive a wee bit into how we built the interpreter and how it actually works. So as I said, it's a bytecode interpreter. You take a function like this simple function here, and this is the bytecode that gets generated for that function. So one of the things you'll notice is it's a register-based interpreter. So you can see operands to these bytecodes, which specify registers in these cases. And for example, so mul R0, R0 is a register, which represents a local variable or a temporary expression that we need to store on the stack. So the way we work is we kind of imagine we have an infinite register file, and we allocate registers as needed. And then these registers, which are not machine registers, they get allocated onto the stack frame when we start. So in this case, this bytecode only uses 1 register. So when the function, in the function prologue, when it starts, we allocate space on the stack for R0. And whenever the bytecode comes in that has R0 as an operand, we know that that's the stack slot that we're talking about. So we initialize it with undefined, which is the JavaScript thing. But there's also other registers here. You can see A0, A1, A2. So these are the things that come into the function. So you have parameters A, B, and C. So they're passed by the callee on the stack as well. And so we can operate on them as if they were registers that we allocated ourselves. So these things have already come into our function. And any bytecode that can take a register can also take a parameter. And finally, you can see things like, so the sub A2, well, sub is a binary operation. Why is there only 1 operand here? So this is because we have an internal implicit register, which we call the accumulator. And that actually is stored in a machine register. And that one is used in many bytecodes as an input or an output or both. So in the case of sub, then one of the inputs, the left-hand side is the accumulator. Sorry, the left-hand side is the register. The right-hand side is the accumulator, and then the output is the accumulator. And so we only need to specify 1 operand to do that binary operation. So our accumulator also starts off as undefined. So I'll just walk through this bytecode and show you what happens on the stack as we go, and how it corresponds to the function, the JavaScript function in the first place. So first thing we do is this LDA SMI 100. So SMI is our name for small integers in V8. So we want to load 100 into the accumulator. And that corresponds with that 100 at the right-hand most side of the first statement. So we end up with 100 in the accumulator when that's executed. Sub A2. So that's going to subtract the A2. Sorry, it's going to subtract the accumulator from register A2. So previously, the accumulator held 100. A2 held 150. So we end up with 50 going into our accumulator. And then we want to store that in variable D. So we've already allocated variable D with register 0. So that local variable is register 0. And we store it into register 0. So that's the 50. Now we go into the next statement. We want to load parameter b. So that's a1, and that goes into the accumulator 2. Then we want to multiply that by r0. So we do that, end up with 100, and then add a0, which is 5, and end up with 105. And then we'll return, which will return the value that's in the accumulator. So you can see here why the accumulator works quite well with this kind of left to right expression of evaluation of expressions. Because we're always keeping we're evaluating the right-hand side first, and then we're keeping the right-hand side in the accumulator, we can work towards the left-hand side and just avoid having to store these things into registers. We just keep operating on the accumulator. So how do we generate this bytecode in the first place? So we need to parse the JavaScript. It generates the abstract syntax tree, the same abstract syntax tree that the compilers use. And then we walk the abstract syntax tree, and we visit the nodes in that tree in order, and generate bytecode for each of those nodes as we go. So that's our bytecode generator part of our pipeline. So for some operations, this is pretty simple. So this is my simple example of add. It's a bit simplified, but it's pretty much what's in the code. So we want to visit the left expression first. We visit it and put it into a register. So we put it into this register left-hand side. Then we want to evaluate right-hand side, and that goes into the accumulator. Then we emit our add bytecode, and we give it ls, the left-hand side register, as its operand. So that will emit the bytecode for add. And then we tell the visitor that the result of our node is now in the accumulator. The add operation puts the result of the add in the accumulator, so we tell that so that any other nodes above know where the result of the previous node, the child node is. So that's a fairly simple one, but they're not always so simple. This is the code for visiting an object literal, and this. JavaScript is complicated. So we generate code in the bytecode generator, and then we feed it through a bunch of optimization steps. So these are inline steps, and we feed it effectively. We feed the pipeline effectively one bytecode at a time, and it works. The bytecode will work its way through the pipeline, sometimes straight through before we start emitting the next one. Sometimes we cache it for a bit to check if we can do some optimizations based on the previous bytecode. So we have various optimizations. I won't go into detail, but basically the register optimizer tries to avoid unnecessary loads and stores of registers. We can avoid it. The people optimizer tries to merge up multiple common bytecode patterns into a single uber bytecode that does all those operations at once. And then we do some simple dead code elimination. If we know there's a return bytecode, then anything else before a branch or a label can't ever be executed, so we can just omit it to make the bytecode smaller. Then we feed that into the bytecode array writer, which writes the bytecode, and then when we want to execute the bytecode, that's fed to the interpreter, and the interpreter executes the bytecode. So I hope you can see here that basically we've generated another compiler. Like, this is a compiler which happens to compile to bytecode rather than machine code. So the actual time taken to compile a particular function is not actually much faster than full code gen. In fact, full code gen is a bit dumber than this pipeline in the sense that it doesn't do any of these optimizations at the top level here. It just spits out machine code. It spits out more machine code, so sometimes that causes it to take a bit longer, but it just spits out bytes in the same way as we're spitting out bytes, just different type of bytes. So what about this red block here, the interpreter? How do we build that? So interpreter, we should build this so that it's platform independent. We could build it in C++, right? Just have a big switch statement with all the bytecodes, execute through them. If you know C++, you can also have a goto label, which is a bit faster way of doing an interpreter. We could do this. The problem is it's slow. And it's probably not slow in the way you think. It's not that the C++ code is necessarily slow. Compilers are fairly good at optimizing these switch statements or goto labels and generating decent code based on them. We could have written that. The problem is that to interoperate with the rest of V8, that becomes slow. So we would need, because the C++ calling convention is completely different from the JavaScript calling convention, whenever we were calling a function, if that function was jitted, we would need to build a trampoline that translates from the C++ calling convention to the JavaScript calling convention. Also in V8, we have a whole bunch of handwritten assembly for various fast path common operations. They're called code stubs. And all of these also would need specialized trampolines to jump to them, or else we just couldn't use them, and we would be a lot slower. So we avoided writing it in C++. OK, don't write it in C++. Hand code it in assembly. This is actually effectively the default option in V8. There is a lot of hand-coded assembly in V8. I had a quick look. There's about 35,000 lines of hand-coded assembly for each architecture. Does anyone who's not on the V8 team want to guess how many architecture ports we have in V8?
5.
It's a good guess. Used to be 5, used to be 6. It's now 9. And I know plans of adding at least one more, bringing it to 10. I don't know about you, but we didn't fancy writing interpreter 10 times. So we didn't do that plan. So what's the other option? Well, we have an optimizing compiler which generates fast code for each of these architectures, the turbofan compiler. And it actually has a pretty nice interface that looks a bit like an assembler. It's a kind of macro assembler. And you could kind of squint and think it looks like you're writing hand-coded assembly. But then you write it once, and it'll generate assembly for each of the architectures. So you have this write once assembly, which is great. You also get the benefit. So we're kind of fitting in just at the last level, the machine level of turbofan. But we still get the last level optimizations of turbofan. So we still get the advantages of low-level instruction scheduling, optimizations, and various other optimizations for free, effectively. So you don't need to hand-code special patterns for particular architectures. And finally, because turbofan needs to call all these stubs and JavaScript functions, the interop problem that we had with C++ just goes away. We've kind of got relatively painless interoperability. And additionally, some of these code stubs are now being built with the same mechanism that we're using for the interpreter bytecode handlers. And so they can just be inlined immediately into the interpreter bytecode handlers, or generated as code stubs if turbofan needs them. So the same code effectively can be both in optimized code and our bytecode handlers. So this is the way we did it, which leads us to the interesting situation now that if you want to port V8, you need to port the optimizing compiler first, then you can port the interpreter. It's pretty interesting. So back to our simple example of add. So what does the add bytecode, the code to generate the bytecode handlers for add look like? So we have these macro instructions where assembler is called. So we want to first get the operand which tells us the register we need to perform add on. So we're getting the index of that register by looking up effectively the next byte in the bytecode. We then load that register, and we get back a turbofan node that represents the value that that load would have had. We want to get the accumulator. That gives us another node. And then we feed them both into the add stub, which generates code to do the add operation in JavaScript. And then we set the result of that operation in the accumulator, which gives it to any of the other bytecodes succeeding us. Finally, we dispatch to the next bytecode. We know the size of our bytecode. We look at the bytecode after that and execute and jump to the handler for that bytecode. So this is pretty nice because we get to reuse this add stub, which is particularly nice when you see that the add stub has 375 lines of hand-coded, again, macro instructions like this, just to deal with numeric operations. But of course, JavaScript add doesn't just work on numerics, it also works on strings. So there's another 250 lines of them. And then there's countless other lines for type conversion. And in the worst case, we'll just give up and go to the runtime and decide that the runtime can do it for us. But you can see why, by doing this, we get to reuse the other stubs that are generated by V8 already into the bytecode handler and effectively get to use that for free. So, some results. Yes?
These lines of code, are these assembly or code?
They are lines like this. So they're C++ code that generate assembly code. It will generate much more actual instructions than 375. Results. So we've been working in the last quarter to make Ignition fast. So you can see over the quarter, this is our Octane score of just Ignition when we disable all the optimizing compilers. And we've doubled the performance of Ignition over the last quarter, which is pretty nice. That's full code gen. So we still have some way to catch up with full code gen. But this is not bad. Like, full code gen is a JIT. We're an interpreter. 2x slowdown is not too bad for an interpreter, and we have plans to eat away at that extra gap. And of course, this is not the full story. You don't run with just the first level JIT. You run with the other optimizing compilers enabled. And as soon as some code gets hot, that's going to get optimized pretty quickly. So this is our performance on Octane when you add in the optimizing compilers. So we've currently got about 20 to 25% gap versus the default pipeline. There are many of the benchmarks which we're effectively equivalent now, and there are occasional benchmarks where we really suffer. And the majority of where we suffer is where we can't get out of Ignition, where the previous pipeline could get out of full code gen and jump to optimized code. So this on-stack replacement thing that I talked about previously. And we're going to work on that in the next quarter. But of course, this is Octane. Octane is not a particularly representative benchmark for websites, and Toon's going to give a talk about that later. But slightly better benchmark for web forms is Speedometer. Here, better is down. It's in milliseconds, and you can see we're much, much closer. So on desktop, we're within about 5% of the score, and on a Nexus 5, it's within the noise. It's within 1 or 2%. So we're reasonably happy with the performance on real-world web pages, and we're still going to do more work on that. But the real benefit comes from memory usage. So this is the amount of code generated for Octane for Ignition versus full code gen on each of the main architectures that we look at. So, of course, the machine code for full code gen depends on that architecture. So you can see we're anywhere with between 2 to 4 times smaller, the bytecode, than the machine code generated by full code gen. But of course, we don't just generate bytecode, we also generate optimized code. So if you put that in with the optimizations enabled and try and load top 10 mobile sites, this is what we see. So we basically half the code size that we generate overall. And that corresponds to a reduction of about 2 megabytes, which you can see is a fairly significant percentage of the V8's heap size overall on these real-world pages. So we're quite excited about this for memory usage, and we have other exciting things that we can take advantage of Ignition for. So I'll just run through those and run through how we're going to take advantage of Ignition further. So as you saw at the moment, our performance is not quite where the default is, but our memory usage is so good that for low-end devices, we think it's better for those users to have the benefits of that low memory, which gives added advantages to user experience compared to the performance gain losses that they would get from running Ignition. So for M53, we're going to launch Ignition on low-end, what we call svelte devices. So these are Android devices that have less than 512 megabytes of RAM, which really suffer at the moment on Chrome. We've already run experiments on dev with this, and we're seeing in the wild about 16% smaller V8 heap sizes, which corresponds to about 8.5% less memory usage in the renderer. That corresponds to an increase in runtime. So this is the amount of time spent in V8 over everything, so parsing, compiling, and running JavaScript. And that goes up by about 14% at the moment. But we're working on that, driving it down. So launch on svelte devices. Then, end of Q3, we want to launch on all devices. We want to replace the full code gen with Ignition for all other devices. And here, what we want to actually benefit from is startup time. But where do we get that benefit? So I already said that compiling and parsing is not actually that much faster in Ignition. And you can see that, so this is this graph that I showed at the start for typical 25 websites again. You can see the pink bar has got longer. Like, we're now spending more time executing the actual JavaScript. And we're not spending that much less time compiling or parsing. But this is using the same lazy compilation method that I talked about at the start. If we instead just compile everything to bytecode, we take a hit on memory because we're compiling more stuff that might not get used, but we drastically reduce the amount of parse time. So you can see even now, if we go in this mode, the reduction in parse time offsets our increase in JavaScript time, and it's the fastest configuration across these 25 websites. And we have a bunch of plans to reduce the size of this pink bar. And you can see also the yellow bar, the compile bar, went up slightly here because we're compiling more code. So we have other things that we want to do there, so compiling and background threads and off the main thread, and that should really help us drive that down as well, and then hopefully we can get some really significant startup wins from Ignition. So that's the end of Q3. At that point, we'll still be using this Franken pipeline. We'll still be optimizing to full code gen and crankshaft and parsing at each of the steps. But the real benefits of Ignition will come in when we can drop the deprecated pipeline and feed bytecode straight from Ignition into Turbofan for the optimization. So that also depends on the work Benedict and the compiler team are doing on Turbofan to really speed that up. But once they have that, we can deprecate crankshaft and full code gen and basically move from this to this. As I said, we already have this working, and what you end up with is the function gets compiled to bytecode, and the bytecode, each of the bytecode effectively ends up being a node on the initial graph that the compiler builds. Those nodes are wired up based on the relationships between the accumulator and the registers and how those would have executed in real life. And so you end up with a graph which would look similar to the graph that you would generate if you parsed and generated the abstract syntax tree in the first case. But once you've done that, you no longer need the JavaScript for optimizing. There are certain situations where you do need the JavaScript source code for toString and things like that, but they're uncommon enough now that we could just get rid of the JavaScript from memory, store it to disk, or re-request it from the network potentially. So doing that, if you look at the size of minified JavaScript, minified JavaScript is actually a particularly dense format of code. It's pretty good at that. Our raw bytecode is slightly smaller than that. And then we need some additional metadata, so constants and source position info for the debugger. When you add that in, we end up being about 1.6 times the size of the minified JavaScript. But if you can throw that JavaScript away, that's still a good win if you keep about all the bytecode for the functions instead. If you tried to do the same thing on full code gen, well, of course, the code in the first place is about 4 times larger than the minified JavaScript. And you wouldn't be able to throw away the JavaScript because you still need to parse. So you end up with more like 5 to 6 times the overhead of the minified JavaScript. So to summarize, Ignition is a fast JavaScript interpreter that we're working on. We've got immediate memory reductions, which we're targeting for low-end devices and M53. And it promises to improve our startup time on high-end devices. That's what we're aiming for in Q3. And it's the basis for our new, simpler compiler pipeline in V8, which is hopefully going to lead to a whole new set of opportunities and optimizations that we can feed into the rest of V8. So I'd just like to thank everyone that's worked on this. So myself, Orion, and my 3 are in the London team and been primarily working on this. And there's a bunch of people, not all who are listed here, but these people have been working closely with us and the V8 team here in Munich have enabled us to build a good product that we can ship. So if anyone has any questions, if we have time, I think we do. Yes?
Probably the classic question for this. How do you handle eval? Do you like
How
do you handle calls to eval? Do you have to rerun the?
So eval, when you call eval, we effectively send the string that you're evaling to the parser and generate code from that. And so each time you call eval, you're going to parse it separately. I think we never optimize eval code because we throw away that string as soon as we've parsed it and can't regenerate the AST. This might give us an opportunity to do that because it turns it into bytecode. Mark? Mark. Mike, sorry.
Hi, yeah. With the bytecode, there's any number of sort of existing bytecodes out there, but it looks like you've chosen to develop your own. Yeah. What were the, I guess, constraints and what were you optimizing for when designing that bytecode?
So we were optimizing for size. Our initial approach was it was exactly for the svelte devices, and then we saw we could get other benefits from it. So these are as small as possible. If you look at JSC and I think even Chakra, they have their own bytecode which is optimized for speed, and they're much larger. They have full words for bytecode operands, which allows them to be a bit faster, but it's much larger. The second thing we were optimizing for was allowing the bytecode to feed the turbofan optimization pipeline. So almost every bytecode corresponds to a high-level JavaScript node in TurboPan. And that makes it really easy to interoperate between the two, because when you're generating optimized code, you have one node per bytecode, and you can work out if you need to de-optimize, was it before that node or after that node? Therefore, it was before or after that bytecode, and we know everything about what the bytecode would execute when doing that. Yes. Exercise.
Hi. When you showed the metrics for the performance on the Svelte devices, and you showed the time of the runtime increasing by 14%, does that correspond closely to battery usage?
It could do, yes. Yeah. There's trade-offs there, of course, though, because so if we manage to avoid the out-of-memory process killer killing a background tab by reducing it by 16% the memory, then we don't need to reload that page when the user switches back to the tab. So that would be a much more energy usage. It's interesting. I don't think we have energy usage on the wild, but we should maybe run some telemetry benchmarks and see if we can get some numbers for that as well. It'd be interesting. And that 14% is not the overall page load time. It's the amount of time in V8. So it's a much smaller proportion than that.
So you just partially answered my follow-up. Do you have an idea of what that corresponded to overall?
It's difficult to say with UMA data, because I don't think we don't track the amount of time we're executing every single task on the main thread. If we did, we could work out the proportion. But get back to me, and maybe we can try on telemetry and get some numbers for some representative pages. Okay. Thank you very much.